So, good morning, students. I'm happy to see you all again. So, am I audible to you? Am I audible to you? And is the screen visible to you? Good morning. So, am I audible to you? And is the screen visible to you? If yes, please say yes. Good morning, Yesh. Good morning, Sirisha. Yes. Okay. So, see here. So basically, we have seen, first law of thermodynamics, correct? So we have dealt first law of thermodynamics for open systems as well as closed systems, and we have calculated different, work and heat interactions that are taking place with respect to the system and surroundings. So one thing that came to the observation was, okay, the construction of a machine or the construction of a device that produces continuous work output. Continuous work output by sole effects of its energy. By sole effect of its own energy, by sole effect of its energy is impossible. Is impossible. Means, good morning, all of you. So see here. So means if you take any system, in general, some random system, of course, it can be closed. Then you can't get continuous work output because see here, the energy of the system, E of the system is finite. Correct? There are practically no systems with infinite amount of energies. So this E of the system means the internal energy that is lying within the system is finite. So this system is capable of producing some work by its own, but it's not possible for the system to produce continuous work output. Means, for example, if you take a turbine, something like this. When you stop, there is no mass inlet to the system, and when there is no mass outlet, then the small mass that is already existing may produce a very minute quantity of work, but this turbine itself is not capable of producing continuous work. Correct? This turbine can't produce continuous work on its own because the energy within the turbine is limited. So any device, it's really impossible for us to construct a device which by its own effect produces continuous amount of work. Correct? If that's happening in your power plant, if you install your turbine, that is sufficient. Why to use boilers, condensers and all these things? Correct? So it is impossible to design such a device, and these devices are called perpetual motion machines. Perpetual motion machines. And these are the machines that violate first law of, that violate laws of thermodynamics. So what are perpetual machines? The machines that violate laws of thermodynamics are called perpetual motion machines, and this is called perpetual motion machine of first kind because if you see, Q minus W is equal to delta E of the system. Correct? So if you don't supply any work input or instead of Q, let us write this: E in minus E out is equal to change in energy of the system. So if you are not providing any energy input for the system, then to get some work output from the system, this should be equal to change in delta E of the system, and this system's energy is finite, it's not infinite to produce continuous work output. Means the machine which operates in this condition is impossible to construct. So these machines are called perpetual motion machines, and the device which doesn't obey or which violate the device or the machine that violates Is it buffering for you? I hope things are fine, Ajay. Please have a look. The machine that violates first law of thermodynamics is called PMM1, means perpetual motion machine 1. So what is the perpetual motion machine 1? The machine should violate first law of thermodynamics, means if this is getting violated practically, then you say the machine is perpetual motion machine, and practically this is not possible, means PMM1 is not possible or impossible, which I have already stated here. Okay, because you can't get continuous work output with the expense of energy of the system, because energy of every system is finite. Okay, so with finite quantity of energy within the system, you can't get continuous work output, which is very large. Okay, practically. So this is a small story about PMM1. Now let us start our discussion with something called second law of thermodynamics. Okay, second law of thermodynamics. Okay, so now let us start. Now let us before straight away working out the equations, let us try to learn some things. Let us suppose there is a room and you put a coffee cup here. Okay, and there is some coffee in this. Of course, it's a hot coffee. So what happens if you talk about heat transfer, and if this is a room which is at a temperature T infinity relative to the low to the coffee temperature Tc, then what happens if you take this complete thing as a system? Some heat gets transferred from the coffee to the atmosphere. Correct? And heat lost by coffee is same as heat added to the atmosphere or surroundings, for example. And this process takes place generally if you put this coffee cup in a room temperature, in a room which is relatively at low temperature, heat from some part of this coffee will transfer to the atmosphere. But now, can I write or design some process like this, where there is a coffee cup again that you are placing, and this time atmosphere is also at T infinity, and this is Tc, which is Tc is greater than T infinity, means coffee is generally at high temperature than at atmosphere temperature. Can I write this like some heat is getting into the coffee from the atmosphere, and heat lost by atmosphere is equal to heat gained by coffee. Heat gained by coffee. So can I write this way? Look, first case is when you put a hot coffee, some heat is getting transferred to the atmosphere. In a second case, you put a hot coffee, which is for which temperature is more than T infinity, and I will tell you that some heat is getting transferred into the coffee, and heat lost by the atmosphere is equal to heat gained by the coffee, which means here also energy is conserved and here also energy is conserved. Whatever the heat that is lost by the atmosphere, that is gained by the coffee. If I say this, mathematically this may support you, but practically if you see, this second process doesn't take place by its own. Correct? Do you all agree with me? Will this second process takes place along with me? Can this second process happen practically? Yes or no? Can this second process take place practically if you see? No, it can't take place. Correct? Which means for the process to happen, it's not only mandatory that it should satisfy first law of thermodynamics, but there is some excess condition that it should satisfy. Correct? If you see, energy is conserved actually, because Q lost by coffee is same as Q added to the surroundings. If you see, whatever energy is transferred from one system, that is completely added to the other system. But if you see, the direction of the process is really important. Correct? Even though it is satisfying first law of thermodynamics, means whatever the heat that is lost by the atmosphere is same equal to heat gained by the coffee. But practically, if you see, this process doesn't take place in nature. Correct? Means there are some processes generally, even if they obey first law of thermodynamics, it does not mandates that the process should happen. Okay, means you should have very clear view about direction of the process, means the direction of this heat transfer in this case. Okay, so generally satisfying first law of thermodynamics is not sufficient for a process to happen. This is what we need to know. Okay, so which means you can write, for a process to occur, due to sun heat, the water in the tank gets heated. Yeah, of course, because water temperature is less than the outside atmospheric temperature in general. But if you see, I told you coffee temperature is greater than atmospheric temperature. Okay, Dinesh? So see here, for a process to occur, it is not sufficient that the first law of thermodynamics alone gets valid. The first law of thermodynamics alone gets valid. Okay, so there is some constraint on the direction of the process, in which direction the process should happen. So if you understand this much, then you can decide one thing: if a process satisfies the first law of thermodynamics, then it doesn't mean that the process happens. Correct? Example in this case. So now, so if you see, this second law will give you the direction of the process, basically means in which direction the process will occur along with satisfaction of first law of thermodynamics. Okay, so for going further, we need to define two quantities called thermal reservoirs. Okay. And here this also brings you one important concept. There is something like reversibility and irreversibility. See, for example, if you discuss the paddle wheel experiment that we discussed during first lecture of concept of heat and work, there if you remember, we have drawn some experiment like this, correct? And we have adjusted a paddle wheel to this, and then we have tied some weight, and we have tied one block, and we told this process is practically irreversible because there is some effect on the surroundings, which means if you rotate this wheel, there is some heat that is added to the system. But in reverse case, if you add heat to the system, this paddle wheel doesn't get rotated. Correct? So these are different, process where it shows reversibility and irreversibility. It means basically this process is not possible. Okay. Next. So thermal reservoirs. So what are thermal reservoirs? Let us define that. The hypothetical bodies that have very large thermal capacity values, very large thermal energy capacity, in bracket, what is thermal energy capacity? Product of mass into specific heat. That can supply or absorb finite amounts of heat without change in temperature. Are called thermal reservoirs. Okay, means this product of this mass into specific heat should be very high, which means in general, specific heats are generally fixed for substances with some finite values. This mass of the substance has to be very huge. Examples, if you go, we don't have exact thermal reservoirs, but practically if you see oceans, lakes, all these things you can take care of. Okay, and practically if you see, it's not actually thermal reservoir, but practically you can for the time purpose you can assume a two-phase substance. A two-phase substance can be relatively treated as a thermal reservoir. Can be relatively treated as a thermal reservoir, because see here, if you heat any pure substance, what happens? Generally, first the temperature of the substance increases, then after during the phase change, there won't be any significant change in temperature, but it's of course other properties changes, but temperature doesn't change for a pure substance. And once the phase change is complete, then temperature again increases. Correct? During this phase change process, if you see, during this phase change process, the substance absorbs energy, but practically there is no temperature change. Correct? Similarly, obeying to this thermal reservoir's definition. Okay, so things like this can happen in our real life, where we are changing the phase of a substance by providing some large amount of heat, but still, our temperature is maintained at the same point. So the thermal reservoirs, that supply heat are called thermal sources, and the thermal reservoirs that absorb heat are called thermal sinks. Okay, so now there is one person named KelvinPlanck. Okay, then this KelvinPlanck told one really good statement. What he observed experimentally was, for any device, if you supply some work, some heat energy, then you will be getting some work output. And he found out for cycles, this Q is not same as this W. Means this total heat interaction is practically not equal to this work output that you are getting. Okay, so this is what he observed. Means if you put 100 kilojoules of work here, of heat here, he observed something less than 100 is coming here. The reasons can be many, because whenever you are supplying this heat has some temperature, of course, and this device is operating at some other temperature. So because of some temperature changes, and since atmosphere is relatively cooler, some part of heat may get transferred outside. So because of some reasons, whatever concerned, he observed experimentally one thing, that whatever heat you supply to a device, the heat cannot be converted to work completely. That's what this much he observed. Okay, and maybe some heat is getting ejected by the device, or some heat is getting ejected to some other part. It doesn't matter. Experimentally, what he found out was, by exchanging heat with single reservoir, means if this is a reservoir, for example, if you put some reservoirs as fuel oils or something like that, whatever heat he is putting, he is expecting something less than this 100. This is what he observed experimentally, and he stated that it is impossible to construct a device that operates on cycle means the work output should be continuous. Whenever you have continuous work outputs, generally you go for cyclic devices, because if you have cycle, because at the end of every process, the system should be capable of again reaching to the same initial state, so that it is again capable of producing a process which is work producing. So if you want continuous work output, the devices should operate on cycle. So it is impossible to construct a device that operates on cycle by exchanging heat or by exchanging energy from a single reservoir. So this is what he told. Means by taking energy from a single reservoir, means it not exchanging heat or energy with any other forms, but it's just interacting only with one reservoir and taking some heat. For example, if you see, this is some reservoir here. Let me draw a big diagram so you can see the things. Means suppose if you have some reservoir here, it is not possible to construct a device of this case. Okay, means which takes energy from a single reservoir and produces continuous work output. Now, devices that produces continuous work output by exchanging heat or energy, by exchanging energy from a single reservoir is called perpetual motion machine of second kind. Perpetual motion machine of second kind. Okay, of second kind, and he told it is impossible to construct such a device. And this statement, what Kelvin-Planck told, is called Kelvin-Planck's statement of second law, because he put, even though you can write energy lost by this atmosphere is equal to work produced by this device, even though the first law appears to be get satisfied, but this process is practically not happening. Okay, so that's why he named this as second law of thermodynamics, and it is called Kelvin-Planck's statement. So this is first consequence of this. First consequence of Kelvin-Planck statement. Okay, else let me I think you can't see that, so let us write it here. First consequence of Kelvin-Planck's statement. And the first consequence is perpetual motion machine of second kind is not possible. Means PMM2 is not possible. This is what he observed experimentally. Next. Now, the condition is when any device you can't produce continuous work output by exchanging heat with a single reservoir, then how many reservoirs we need? So minimum there need to be 2 reservoirs such that this is reservoir 1. When you connect this to a device, some device, let us suppose this is operating and producing continuous work output, and let us suppose there is another reservoir 2 here. Reservoir 2. So which means some part of the heat that is being taken from this reservoir is rejected to another reservoir, and this device is capable of producing continuous work output now, correct? Because he told if there is no single reservoir, this process can't happen, correct? Means whatever the energy that is coming here can't come out work as completely. So what he decided was there should be some second reservoir so that some part of the heat where it is ejecting, let us assume that part of the heat is going into the other reservoir with the effect of the device producing some work output, and this gave the concept of heat engines. Concept of heat engines. Because when you can't exchange heat with a single reservoir and you can produce complete work, continuous work output, definitely there should be some second reservoir too, so that some part of the heat that is supplied to the device gets ejected. Okay? So this is the second consequence of this Kelvin-Planck statement, concept of heat engines. And this heat engine is a device. If you want, you can write heat engine is a device that produces, okay, you can write the statement this way, that converts thermal or heat energy to mechanical work by exchanging heat with a minimum of two thermal reservoirs. A minimum of two thermal reservoirs. There can be three, no issues. But with one, you can't produce continuous work output. That's what it was told. A minimum of two thermal reservoirs. So this is the concept of heat engine. Means we can design a device which can produce continuous work output by exchanging heat with minimum two thermal reservoirs, out of which one can put in heat intake and one will be definitely, there will be some heat loss from this device as well, because this QH can't be equal to W. So whatever energy that is coming into the device, that is equal to work plus some other rejection from the device. So this gave the concept of heat engines, and we say if QH is the heat supplied by thermal reservoir 1, and QL is the heat rejected by the device, or you can say heat ejected by the engine, since we introduced the term heat engine. Heat ejected by the engine to the thermal reservoir 2 to the thermal reservoir 2, then means if you have this case where you have some thermal reservoir 1 from where you are taking some heat and giving it to a device that operates on a cycle, or you can write directly heat engine, and if this heat engine is providing some part of the work by exchanging heat with another thermal reservoir, which is like reservoir 2 for example, this construction is possible as per this Kelvin-Planck statement. And now this construction, this heat engine, when it's given QH amount of heat, out of this QH amount of heat, some heat is getting ejected to another thermal reservoir, but some part of this heat is being converted to work. Which means if you talk about efficiency of heat engines, for the first time I'm using this word, efficiency of heat engine. Efficiency of heat engine is equal to, the definition for efficiency is equal to work output divided by, or you can write desired output, better, desired output by required input. Correct? Generally, what is the efficiency? For the given quantity of input, how much we are getting it as desired output. Means, for example, if you are supplying heat, out of this heat, how much amount of energy is coming out as work. So in this case of heat engine, eta means efficiency of heat engine is equal to desired output is this work, because your main motto by constructing a heat engine is to get some useful amount of work. So W divided by what is heat input that is required to produce this, get W out, which is QH. Now, if you apply first law of thermodynamics, since cyclic devices they operate at steady state in general, this energy into the system minus energy out by the system is equal to change in energy of the system. Correct? Means basically E in minus E out is equal to delta E of the system. But if cyclic devices generally, if you see, they operate on steady state, so there won't be any change in energy of the system. So this implies E in is equal to E out, which means QH, what are the heat that is being added to the system, should be equal to W plus QL. Means this part of heat is getting, some part of this heat is getting converted to work, and some part of this work is, some part of this heat QH is also being ejected to some other reservoir. So QH is equal to W plus QL as per first law of thermodynamics. This is as per first law. So if you see, this W which is here can be written as QH minus QL. So eta of heat engine is equal to QH minus QL divided by QH. So if you take QH common, we have 1 minus QL divided by QH, and this is the efficiency of the heat engine. Okay, so which is basically 1 minus the ratio of heat lost by the device or heat ejected by the device to the heat supplied to the device. So we see efficiency of heat engine is equal to 1 minus QL divided by QH. Okay. Now, if two engines are operating in series, what happened? Okay, so see here. If two heat engines are operating in series, if two heat engines are operating in series, means what's the definition of this? What's the meaning of this? If you have this as reservoir 1 and this reservoir 1 is supplying some amount of heat to this cycle heat engine 1, and this heat engine 1 will eject some heat, of course. This is QH. Let us suppose this is QM and the work that is produced is W1. Next, this QM which is ejected by this heat engine, sorry Vamsi, you said? No, this is for the first law of thermodynamics. If you take for this system alone, see, I'm talking first law of thermodynamics for this system. Okay. What I told is this QH can't be equal to W alone. Okay, that's what I told. Whatever the heat you are supplying can't come out as work. So QH is not equal to W. QH is equal to W plus some other quantity. Okay. Even though if you see QH is not equal to W here. Clear? So this QM which is ejected by this first heat engine is taken by second heat engine HE2, and let us suppose this is producing a work output W2, and finally, let us suppose this is ejecting this to this reservoir. Okay, so means whatever the heat that is giving is taken by this. So if these two heat engines are operating in series, for that simplicity, you can assume one more thing. Let us suppose this QM which is coming here is being sent to a thermal reservoir again, reservoir 2, and same amount of heat QM which this thermal reservoir is taking is again supplying for this QM. Then this will be reservoir 3. Okay. So if this is the case, means this heat engine is operating under two thermal reservoirs, and this heat engine is also operating under two thermal reservoirs, and this reservoir 2 which is here, when it is getting a amount of heat Qm from this heat engine 1, it's directly delivering that Qm to this heat engine for the work output. So if this is the case, if you want to talk about efficiency overall, means overall efficiency of this engine, see here, this is equal to what is the total work that you are getting from this combined engine. First part of work you are getting here, okay, first part of the work you are getting from here, and second part you are getting here. So the total work output you are getting from this device is W1 plus W2 by what are the heat input that you are actually providing. Of course, this Qm is a part of this QH which is being sent to this second reservoir. So the total heat that you need is QH. Okay, this is what we had. So this is equal to W1 by QH plus W2 by QH. Now you have this particular expression with you, yes or no? So now let us try to see what is this W1 by QH. This W1 by QH can be represented as efficiency of heat engine 1 plus, yes or no, because W1 divided by QH is nothing but directly the thermal efficiency of this first engine, plus this W2 by QH. This QH can be written as Qm into Qm divided by QH. Correct? Because we don't have any direct relation between this W2 and this QH. So let me make some small manipulation in the mathematical terms. So see here, for this, see Qm is equal to, see W2 by Qm is equal to eta 2, correct? So if you see, this is equal to efficiency of heat engine 1 plus efficiency of heat engine 2 into, see this Qm by QH. If you see the first heat engine, efficiency of heat engine 1 is equal to 1 minus Qm divided by QH. So what can we write in place of Qm divided by QH? 1 minus efficiency of heat engine 1. So this is what you can write as Qm by QH. So if you substitute that here, 1 minus efficiency of heat engine 1. So if you simplify the terms, overall efficiency of heat engine is equal to efficiency of heat engine 1 plus efficiency of heat engine 2 minus efficiency of heat engine 1 into efficiency of heat engine 2. That's what you'll be getting. See here, because eta of HE2 means efficiency of this heat engine 2 into 1 minus this efficiency of heat engine 1 will give you 1 into this efficiency of heat engine 2 is n eta 1, I mean eta 1 plus eta 2 minus eta 1 into eta 2. And if you see, when two thermal heat engines are operating on series, definitely the overall efficiency of the engine is equal to efficiency of the first engine plus second minus product of first into second. And this formula is a bit important in gate examination because they are setting few questions on this. Okay, so we have seen generally if two thermal heat engines are operating in series, means when first engine is exchanging heat between two thermal reservoirs and second heat engine is also exchanging heat between the two thermal reservoirs, then if W1 and W2 are the work outputs in the first case and in the second case, then we know this is the overall efficiency because this is the total work output that is produced by the engines with respect to this QH. Okay. So did you all understand this? How did we get this expression? Eta 1 plus eta 2 minus eta 1 into eta 2. Yes? I want others to respond. All of you, please respond. Did you all understand why this efficiency of overall heat engine can be equal to this? Okay. So see here. Now, let us talk about one other person, Clausius. He also observed something and he also stated a postulate. Clausius statement. What Clausius told? If you look at the coffee example, heat can't flow from low temperature to high temperature by its own, correct? Because heat is a thermal energy which flows from high temperature body to low temperature body, correct, by its own. But that's what he observed actually in the beginning, and he told it is impossible to construct a device to construct a device with no external effect, other than transferring heat from a lower temperature reservoir to a higher temperature reservoir. Means if you take a temperature reservoir which is at TH, and if you design a device, some device, we don't know what it is, and this device is attached to, okay, space is a bit less, so let me shorten this. Okay, so see here, so this device is not capable of transferring heat from this lower temperature to higher temperature with no external effect. Okay, means without experiencing some work input or some other form of energy input to this device, there can be no device which can transfer heat from a lower temperature reservoir to higher temperature reservoir. That's what he told. Means this QL can't be equal to QH. This is what he told, and this construction is impossible if TL is less than TH. That is what he told. And of course, it's a practical experience. Like no device, generally without any work input or something, generally heat is not capable of flowing from a low temperature body to a high temperature body without any external effect. If you produce some external effect, which I have stated here, this external effect, if you produce on this device may transfer heat from lower temperature from a lower temperature reservoir to a higher temperature body. But in general, without any external effect, there can't be any device which can transfer this heat from lower temperature to higher temperature. This is what he observed, and practically that's true, correct? Because heat always tries to flow from high temperature body to low temperature body, and this temperature difference is the virtue for the heat transfer to occur, correct? So this is what he observed. So this thing gave the concept of refrigerators and heat pumps. Refrigerators and heat pumps. Now, what does a refrigerator do generally? If you see a refrigerator, and this is your atmosphere, and this is the temperature inside your refrigerator, TR is less than T infinity. But still, it tries to transfer the excess amount of heat that is inside to the surroundings by some external effect, correct? So this is what this Clausius statement gave an idea for. So see here, if there are two thermal reservoirs, reservoir 1 and of course which is at a higher temperature TH, and there is one device and it is connected between another thermal reservoir as well. So reservoir 2 TL, and TL is less than TH. Now what he told, this QL and QH, this is not possible without any external effect. But if you produce some external effect, means if you are capable of producing some external effect on this device in form of some energy, then this is possible, because with some external effect your heat can flow from lower temperature body to a higher temperature body. And this gave the concept of refrigerators and heat pumps. And as for heat engines we have efficiency, we can see coefficient of performance for refrigerators and heat pumps. Coefficient of performance. So now if you see what is the coefficient of performance, again for refrigerators and heat pumps, see efficiency is nothing but for the given input how much output that how much output the device is capable of producing. Similarly here if you see the coefficient of performance means how well the device is performing, means for a given energy input how well the device is performing. So COP definition is same as desired output to the required input, So if you see, if you are making this device to work as a refrigerator, means your main interest is to take heat from a lower temperature body to still further, like in case of applications of a refrigerators. If you see, if you take a refrigerator as we have done before, this temperature will be T refrigerator and this temperature is T ambient, which is of course T ambient is greater than T refrigerator. But if you see carefully, the heat gets out of this refrigerated space, which means from a body at lower temperature, we are still taking out some heat by providing some input to this device. And if this is refrigerator, COP of refrigerator is equal to, now out of these two, which is the desired output, we want to take this heat out from this source, which is at a lower temperature. So if you see, this QL is the desired output when we are running this device as a refrigerator, because from the space which is already cooler, we want to take still some more heat to maintain the space at this temperature. So if I doing that, the required desired output that you are going to take out is QL divided by, now to get this QL, what's the energy input that you are giving to this device? This external effect, means this work here. Basically in case of refrigerators, your electrical work which you run the compressor. Okay, so if you see, this is work. This is the coefficient of performance of a refrigerator. And if you see coefficient of performance of a heat pump, and what is a heat pump generally? Which adds heat to a body which is already at higher temperature. Cycle of operation is same. So if you see here, this QH is the effect that is needed, because in cold countries, whenever the room temperatures are very low, they operate these heat pumps. Like how in India we have these air conditioners which tries to maintain the room at a lower temperature compared to the surroundings. In colder countries where temperatures are in minus degrees centigrades, or very low temperatures in general, they'll work out these heat pumps so that this device will add some heat into the atmosphere. Basically, you have this device like this, atmosphere, then your device, this will send heat to your home. Okay, so this will add heat into your home. So as a result, your temperature inside the house is comfortable for you to live. So if you see this coefficient of heat pump, here the desired effect is this QH, because this is the heat that you are expecting this device to add to this particular body. So this is QH, and the same thing that you are giving is W. So there are two devices which work on same principle of operation. One is heat pump and the other is refrigerator. So which in generally one adds heat to the higher space and the other takes heat from the colder space. So now if you try to look at the relationship between these two things, means generally if you have some reservoir at reservoir 1, then you have some device, and then you have some reservoir 2. Let us suppose this reservoir is taking out, this device is taking out some heat QL and moving it to a higher temperature body by taking out some external effect. So if you see, this is TH and this is TL at temperatures TL, then COP of refrigerator is equal to desired output is this taking out of this heat from a temperature, from a body which is at lower temperature. Of course, this TL is greater than TH. TL is less than TH. So if you see, this COP of this refrigerator is QL divided by W, and COP of this heat pump is equal to QH divided by W. Now, if you apply first law of thermodynamics for this device, energy input should be same as energy output, which means this QH which is going out of the device should be equal to summation of all the energy inputs to this device. So which means QH is equal to QL plus W, and this is as per First law of thermodynamics. First law of thermodynamics. So if you see this, COP of heat pump is equal to QP by H. Now see carefully. If I talk about this term, COP of heat pump, QH can be written as W plus QL because of this divided by W. So this is equal to 1 plus QL divided by W. So this is equal to COP of heat pump is equal to 1 plus this QL by W term is mathematically equal to COP of refrigerator, which is working under same temperature limits. So this is equal to COP of refrigerator. So if the same device, if it's working as a heat pump and a refrigerator, COP of this heat pump is equal to 1 plus COP of this refrigerator. Okay, and next, if you see this value once again, W plus QL divided by H, or this is QH by W, this is equal to 1 by W by QH. Correct? Because this QH by W can be written as 1 by inverse of this term, which is W by QH. And if you see, this is the expression for efficiency of the heat engine operating between same temperatures. But in this case, this work is given and the process is and the cycle is in reverse direction. Okay. So if you see this COP of heat engine, COP of heat pump is equal to 1 by efficiency of heat engine working under same temperature limits. Okay, and this is equal to 1 plus COP of refrigerator. So COP of refrigerator is equal to, COP of refrigerator is equal to 1 minus 1 by efficiency of heat engine. Oh, I'm sorry, this is with a minus sign. So 1 by efficiency of heat engine minus 1. So all these are formulations that could help you out in solving few problems and actually finding the exact rates. Okay, so let me summarize. COP of refrigerator is equal to COP. Okay, let me write heat pump and then refrigerator here. So COP of heat pump is equal to COP of refrigerator plus 1. COP of heat pump operating between same thermal sources is equal to 1 by efficiency of the heat engine that operates under the same thermal reservoirs, and COP of COP of this refrigerator is equal to 1 by efficiency of this heat engine minus 1. So these three formulations are really important for us that could help us in solving gate problems a bit. Okay, so now if you okay, so is it clear to all of you till this point? Did you all understand how these three formulations are valid for this device, which is taking some external effect and taking out some heat from a lower temperature reservoir and supplying it to the higher temperature reservoir? Correct? So now, okay. Now, if the device is operating under a reversible cycle, if the device is operating under a reversible cycle, then the ratio of heat interactions of the device with the thermal reservoirs is same as the absolute temperature ratio of the reservoirs. Absolute temperature ratio of the thermal reservoirs. And if, for example, this is reservoir 1, of course, at a temperature TH, let us suppose there is a device that is taking some QH amount of heat, then producing some work, and then again, rejecting some part of the heat to the reservoir 2, and this portion is QL. So means if there is some device that is working between two thermal reservoirs, of course this temperature is TL. Then if you see this, the ratio of heat interactions of the device with the thermal reservoirs means magnitude of this QL by QH is same as TL by TH. This was proposed by Lord Kelvin, and this is called absolute scale of temperatures. Absolute scale of temperatures. Till now I told you the device need not work reversibly, but if there is some reversible cycle that this device is undergoing, means if this device is undergoing a reversible cycle, we can add a word here which is reversible cycle. Then this is called absolute scale of temperature, and actually here this can be any function in terms of TL and any function in terms of TH, but this was purely arbitrary, that was proposed by Lord Kelvin, because we have achieved such condition where this should be same as TL and this is some function of TH, where the choice of this function can be arbitrary. So I'm not dealing this now, but actually as per Kelvin's scale, we should have something like this. When a cycle is working under reversible process, QL by QH should be same as some function of TL divided by TH, and this TL by TH is purely arbitrary choice. Okay, it was proposed by Lord Kelvin, and this TL by TH doesn't have any standardization for such particular ratio, but since we have only thing like this QL should be a function of TL alone and this QH should be a function of TH alone, this ratio is taken equal to this, and this is called Kelvin scale of temperatures. Okay. Now, if the heat engine is undergoing a reversible cycle, with by exchanging heat with two thermal reservoirs, at temperatures TL and TH. Means, for example, if you see, this is reservoir 1 which is at a temperature TH, and this reservoir is supplying some heat to a device or heat engine. Of course, it's a reversible heat engine, which means a reversible heat engine is the heat engine in which the complete cycle is reversible, means the cycle of operation of this heat engine is reversible. So this produces some work and then some part of energy is coming out. Reservoir 2, which is at a temperature TL. So if this is the case, we got the expression for efficiency of this heat engine as efficiency. We have efficiency of heat engine is equal to 1 minus QL divided by QH. This is what we obtained when we derived the formula for efficiency of the heat engine. Now, if the case is, if the heat engine is reversible, means reversible heat engine. If this is the case, then 1 minus, when things are going reversible, this QL by QH ratio can be replaced with TL by TH. And you know, the reversible heat engines gives maximum efficiency because there's no irreversibility that's happening in the process. So, max possible efficiency. Max possible efficiency for a heat engine is 1 minus the temperature ratio. Okay, actually cannot propose this cycle, but we'll see what is Carnot cycle and all we'll see later. But as per absolute scale of temperatures given by Lord Kelvin, this QL by QH can be replaced with this TL by TH. And you know, this reversible heat engine, you know, if you take a reversible device and an irreversible device, it's obvious that the reversible device produces major work, correct, when compared to the irreversible heat engine, because of irreversibility, some part of the fraction of heat that you are supplying gets wasted. So if you see here, this QL by QH can be replaced with this TL by TH, and this is as per absolute scale of temperatures by Kelvin. Absolute scale of temperatures by Kelvin or Lord Kelvin, okay, by Lord Kelvin. Yes, both are different, Vijay. So see here. So you know, a reversible heat engine produces maximum work output for a given heat input, correct? Because there is no irreversibility that is sustaining to waste some part of this heat. Okay. So if this is the case, then let us look at the expressions for coefficient of performance of reservoir, heat pump, and all these things as well. So if you see, if you have a thermal reservoir, something like this, reservoir 1, which is at a temperature TH, and then let us suppose we have a heat engine that produces some work, and a heat pump or a refrigerator, for example, which again works between these two devices, and a heat pump which are operating between the same thermal reservoirs, reservoir 2 at a temperature TL, and of course TL is less than TH, temperature of the lower temperature body and temperature of higher temperature body. Okay, so if you see, let us suppose this heat engine is receiving some QH amount of heat and ejecting QL amount of heat by producing some work output. Okay, and this, let us suppose this refrigerator, by taking some work input, it's pulling out QL to this QH. Similarly, the case with heat pump, by taking W, it's sending QH amount of heat to this reservoir. Okay, so if this is the case, see, the expression for efficiency of heat engine is 1 minus QL divided by QH, and we got COP of heat engine is equal to, COP of heat pump is equal to 1 by efficiency of heat engine, correct? Now, if all these three are reversible, means this is a reversible heat engine, and this is a reversible refrigerator, and this is a reversible heat pump. Then if the heat pump, heat engine and the refrigerator are reversible, then we have efficiency of reversible heat engine is equal to 1 minus TL by TH. This is what we have. Correct? See, KelvinPlanck told any device can't have 100% efficiency. Means whatever the heat you are supplying, that can't be equal to 100. Means basically this efficiency can't be equal to 1. Now this absolute scale of temperatures give you a value for the maximum efficiency of a reversible heat engine or a maximum efficiency of any possible device that is operating between two temperatures TH and TL. Now, COP of reversible heat pump is equal to 1 by efficiency of reversible heat engine that is operating between the same temperature limits. So if you compare this value, this is TH minus TL by TH. So this value will be TH divided by TH minus TL. Correct? And you know, COP of refrigerator is equal to 1 by efficiency of reversible refrigerator is equal to 1 by efficiency of reversible heat engine minus 1. So 1 by efficiency of reversible heat engine is equal to TH by TH minus TL. So this is TH by TH minus TL minus 1, which could give you TL by TH minus TL. Okay, so this is COP of the reversible refrigerator. So this is the formulation for COP of reversible refrigerator, and this is the formulation for COP of reversible heat pump, and this is the formulation for efficiency of a reversible heat engine that's operating between two temperature limits or two thermal reservoirs, which are basically at temperatures T1 and T2. Okay, so now if you know the temperature limits, you can guess all the efficiency terms and the performance terms of the devices. Okay, so based on this knowledge, now let us again look at engines operating on series. Engines operating in series. Engines operating in series. So let us suppose there is a thermal reservoir at temperature TH and there is one reversible heat engine which produces some work output W1 and rejects heat to a temperature source at Tm, and this thermal reservoir will again deliver some heat to a reversible heat engine 2, and this produces work output W2 and again rejects some part of the heat to reservoir at TL. So these are three thermal reservoirs basically. So if you want me to write reservoir at TH temperature, reservoir at Tm, and this is reservoir at TL temperature. Okay, so if these are three different thermal reservoirs that are three different temperatures, let me write this TL clearly so you can see TL. Now, if this is the case where this heat is QH and this heat is QM, so this heat will be QM because whatever the energy that gets into the reservoir, we are assuming that's coming out, so QL. So if these are the cases like this, if two reversible heat engines are operating in series, then first, for both the heat engines, to have same thermal efficiency, So for both the heat engines, if you want to have same thermal efficiency, look, efficiency of reversible heat engine 1 should be equal to efficiency of reversible heat engine 2. And you know, since these both heat engines are reversible and first heat engine is operating between the temperature limits Tm and Th, and second heat engine is operating between the temperature limits TL and Tm. So if you see, 1 minus Tm divided by Th should be equal to 1 minus TL divided by Tm. So if you compare these two equations, we have Tm divided by Th is equal to TL divided by Tm. So this implies TL square is equal to Tm square actually. Tm square is equal to TL into Th. So this implies Tm is equal to square root of TL into Th. Means for both the engines to have same thermal efficiency, the mean temperature of this thermal reservoir should be equal to the geometric mean of this, source of the reservoir and sink of the, source of the heat engine 1 and sink of the heat engine 2. Okay, so did you all understand this? Why for both the engines to have same thermal efficiency, when both are reversible heat engines, this temperature Tm should be equal to the geometric mean of these two temperatures, TL and TH. Clear to all of you? Yes or no? Please respond. Did you all understand why for both the heat engines to have same, this? Okay, so now we'll look at the case. Other case. So see here. For both the heat engines to have same work output, for both the heat engines to have same work output, you please try and tell me what could be the value. See, for same efficiencies, we got this as geometric mean. Now tell me, for same work output between the two engines, what could be the case? Let me draw the diagram meanwhile and you try. This is QL. So this is reservoir 1 at TH and this is reservoir 2 at T2 and TM, and this is reservoir at TL. So please, if for both the work interactions to be same, for both the engines to have same work output means for W1, okay, let me change color. For W1 is equal to W2. See, for both the engines to have same thermal efficiencies, we have seen something like Tm is equal to, this is root of TL into TH, means this is geometric mean of the temperatures, correct? If this is at higher temperature Tm and this is at temperature TL, so Tm is equal to square root of TL into TH. This is what we obtain when both the engines should have same thermal efficiency. Deepak, now what could be the case? This is correct, arithmetic mean. So if you see, this W1 is same as efficiency 1 into QH, and this W2 is same as efficiency of 2 into QM, correct? So this implies efficiency 1 into this QH can be written as QM, just a second guys, I think we made small thing here. Okay, so see here, this W1 can be written as QH minus QM, and this should be equal to W2 is same as QM minus QL. So this implies, if you divide this whole with QM or QM, QH by QM minus 1 is equal to 1 minus QL divided by QM. This is what we have. Now since both the heat engines are reversible heat engines, and for reversible heat engines, this heat transfer ratio, this heat interaction ratio is same as this thermal reservoir temperature ratio. So this TH by TM can be replaced with TH by TM minus 1 is equal to 1 minus TL by TM. So now you can simplify the things and you can tell me. Okay. Any responses from your side? Can you simplify this expression? So if you simplify, TH minus TM divided by TM is equal to TM minus TL divided by TM. And since this is a non-zero, we can cancel this. So if you simplify this TM, when it goes to the other side, we have 2TM is equal to TH, and this TL, when we have negative sign and if it's shifted, you will be having positive sign. So this implies TM is equal to TH plus TL divided by 2. So this is the mean temperature for both the engines to have same work output. Okay, so there are a lot of gate questions that came on these two. Basically, when the engines have same efficiency, of course, reversible heat engines, and this is the case when both the reversible heat engines have same work outputs. Okay, so if you want, you can summarize. For two heat engines operating between operating in series, for two heat engines operating in series with the highest and lowest temperatures, with the highest and lowest temperature range of operation, as TH and TL respectively, then the mean temperature for both the engines to have same thermal efficiency is Tm is equal to square root of TH into TL, which means geometric mean of temperatures. Please write this statement along with me, all of you. Geometric mean of temperatures and for both the engines to produce same work output is Tm is equal to TH plus TL divided by 2, which is arithmetic mean of temperatures. And this is arithmetic mean of temperatures. Okay, so did you all understand why these two situations are arising? Basically for this and the other one ahead. Okay, so any doubts in today's class till this moment? Did you all understand? If you want, we can go for a quick review of the things. Okay, so see here. So we have stated what is PMM1. Basically, the PMM1 is the device which produces continuous work output by its own effect without taking any external help. Then we have stated what is second law of thermodynamics. Then we have seen During the process, it's not even sufficient, it's not alone sufficient to satisfy the first law of thermodynamics, but also it should satisfy something else, correct? And then we went for what is the definition of thermal reservoirs. Then we have seen definitions of source and sink. Then we have seen what is Kelvin-Planck statement. Basically, that gives a rise for the perpetual motion machine of second kind, which doesn't produce 100% of this energy input as the energy output. So if you see, it doesn't convert complete heat energy into mechanical work. So that gave the rise to the concept of heat engines, because when this device is not capable of producing continuous work output, definitely it should exchange heat with the second reservoir. Then by the definition of that, we have defined what is efficiency always for different devices like heat pumps. Then we have seen if both the heat engines are working in series, then the combined efficiency or the overall efficiency is efficiency of 1 plus efficiency of heat engine 2 minus efficiency of heat engine 1 into 2. And then we have defined what is Clausius statement of second law. Then we have seen coefficient of performance of this refrigerator and heat pump, and we have sorted out different relations between COP of heat pump, COP of refrigerator, and efficiency of heat engine. So if one of them is given, we can trace the other two. Then we have seen absolute scale of temperatures by Lord Kelvin, in which this QL by QH ratio means the ratio of heat transfers is same as the ratio of this temperature difference. Actually, I didn't derive with this because even though I derive, there comes a point where I need to choose this TL by TH as purely arbitrary. There is no logical reason behind that. Okay, since they adopted that, we need to follow this. So I didn't give you the derivation for this. So now, if by assuming reversible heat engines, we have seen what could be the maximum possible efficiency, and reversible heat engines will give you the maximum possible efficiency. And then we have seen for COP of reversible heat pump, reversible refrigerator, and all these things. And then we have seen when two engines are operating in series, what's the condition for both the engines to have same thermal efficiency, and then for both the engines to have same work output. And that's what we have summarized. Are you all clear so far till this moment? If you are okay, then I would like to end up this session. It's 11:25. So is that okay to all of you? If there is any doubt, you can talk to me. Open systems notes I will provide today. Because of some issues I couldn't provide in the last class. I'll provide today, Vamsi, no issues. Okay, so apart from that, is everything fine? Okay then. Arithmetic and geometric difference. What's okay? I think we need to look at a bit mathematics for doing that. If generally A, B, C are in AP, means in arithmetic progression. If this is in arithmetic progression, progression means generally series. Okay, and what is this arithmetic series? If you have this ABC in arithmetic progression, then B minus A will be same as C minus B. Means the difference between these two terms is same as the difference between these two terms, Chinaro. So then this B is called arithmetic mean of A and C. Arithmetic mean of A and C means basically the difference between every two successive terms is same. So if this is the case, then B minus A is equal to C minus B, then if you shift this B this side, 2B is equal to A plus C, and B is equal to A plus C by 2. And this is what you call this as arithmetic mean. Okay, geometric mean, if you see A, B, C are in geometric progression, for example, geometric series, then this B is called geometric mean, which is GM. And geometric series, you call this as geometrical series. AR square series of this format is called geometrical progression. Means ratio of every two terms, means B by A is same as C by B, same as D by C. So similarly like that. So if you see, B square is equal to AC and B is equal to square root of AC. Okay, and this B is called geometric mean, which is square root of product of these two things. Vamsi, difference between ppm 1 and 2. 1 tells us without any external agent, the device cannot produce continuous work. PMM 2 tells that even after receiving energy from single reservoir, device can't produce continuous work. In the PMM 1, definitely without any external agent, it can't produce continuous work output. But in PMM 2, even after receiving energy from a single reservoir, it can't produce continuous work output. Okay, so that there is a difference between heat energy inputs. Okay, in PMM1 there is no energy input to the machine. In PMM2 there is at least one, only one energy input to the machine. Okay, clear? Yeah, you can run any heat engines, but definitely this amount of QM QL keeps on decreasing as the engines gets increased. Okay, and finally the last engines couldn't have much impact. Means, for example, see Deepak, I will tell you. This QM is generally very small when compared to this QH, and this QL is really small when compared to this QM. So if you put one more engine, the amount of heat that this TL supplies to that heat engine will be very less, which means the work output supplied by that engine will be very less. So in general, practically purpose, if you see, they'll put two engines in series in general. Okay, like when I deal vapor cycles and Brayton cycles, I'll let you know one example. Generally, they'll combine one cycle with the other cycle so that they can compensate the effects. So I hope we are clear so far. So anyhow, this is not part of this course, so I'm just chopping off. Okay, then we'll wind up this session. Thank you all.